So let's talk about volume of a pyramid in context of triple integrals. So I'm going to make this, let's make this 0. We'll make this 1 and -1. This will be 1 and -1 in the y direction. So the red thing is a 2 by 2 square in the xy plane. I don't know if you can see that well. And the gray things are supposed to come up out of the xy plane. This is the point 0, 0, 1, so on the z-axis. And then the height of the pyramid is also 1. So, if you remember from geometry class, maybe you don't, but the answer is supposed to be area of the base, which is going to be 2 times 2 is 4, times 1/3 times the height, which is 1. So we're expecting an answer of 4/3. Hopefully we can get that. And the integrals are actually one way to derive that formula. All right, so let's do this with a triple integral. What are we doing? By the way, notation, we're going to integrate over, usually we'll say E, so volume is the triple integral over some three-dimensional region E of 1 dV this time instead of dA. Okay, and we're wanting to do this in rectangular coordinates, so we're going to have 1 dx, dy, dz. Okay, let's work from the outside in. So z is going to go from 0 to 1. And then for each value of z, we're basically taking a slice, right? So let's pick a value of z, and then we've got, I don't know if I can draw this, but we've got some square that's a slice of the pyramid. And how big is that square? Well, it gets smaller and smaller as z gets bigger, and it starts as a 2 by 2 going from -1 to 1. So I'm going to claim that these are going to go 1, it'll be going from -1 minus z to 1 minus z in both the x and the y directions. 1 minus z. Let's make sure we agree with that. So we're starting at the bottom, going from -1 to 1 when z is 0. And then we're getting smaller and smaller. It's linear. We have to end up, these numbers have to be 0 by the time z gets to 1. All right, there are a little more methodical ways to do that, but that's kind of the simplest way to think about it. Okay, let's do this integral then. So we're integrating from 0 to 1. We'll leave the second one alone also. Negative, this 1 minus z to positive 1 minus z. And then we will take this integral with respect to x of 1, which is just x, of course. And now x goes from negative 1 minus z to 1 minus z. You don't have to write the x equals if you don't want to. I think it's a little bit clearer, especially your first couple times if you do. Okay, we have to plug in the bounds, 0 to 1, negative 1 minus z to positive 1 minus z. Still, this is going to be 1 minus z minus negative 1 minus z, so basically we'll get a factor of 2 there. dy, dz. Okay, now we integrate with respect to y. This thing doesn't have any y's in it, so that's easy. 2 times 1 minus z. We're just going to get y. And then y goes from negative 1 minus z to 1 minus z. And then much the same thing before as we plug in the bounds. We're going to get this top one minus negative, same thing. So we'll get another factor basically of 2 times 1 minus z. So that's what it ends up being. And then let's expand this so that we can integrate. So 4 minus 8z plus 4z squared dz. Let's integrate that. So this is 4z minus 4z squared plus 4/3 z cubed. And that is going from 0 to 1. So we'll put in 1, we get 4 minus 4 plus 4/3, put in 0, we get 0. So the total answer is 4/3. And we said at the beginning from geometry that that's what we expect. So that's good. We got our 4/3 down here. Okay, so we did it. We did our first triple integral. let's just go back and think about back in Math 125, or the first place you learned how to do an integral, how we would do this problem. Because you can do it. You can, what's the best way to slice it? It's exactly how we did it. We should take horizontal slices and let z go from 0 to 1. And then what is the area of each slice? Well, we've already calculated that. We said that distance across, we just have to do a little bit more thinking. That distance across is now 2 times 1 minus z, right? Because it goes from negative 1 minus z to positive 1 minus z. So we get 2 times 1 minus z squared dz. That's how you'd set that up in Math 125. So this kind of feels like a word problem. That setup was annoying. It's maybe more difficult to get right than some of those plug and chug problems, but you notice that that is the exact same as this line. Okay, so it's good. The answer is going to be the same. And maybe it feels harder. Maybe it feels a little bit easier to do it the Math 125 way because you don't have all this notation. So this is a common theme in math. You can trade thinking for tons of notation. There are uses to triple integrals. For example, if it said the pyramid had density, let's say x, y, z, at any point x comma y comma z inside the pyramid, and then the question was find the mass. Remember I said all the applications still work. So then we would get mass was the integral. I won't plug in the bounds just so that we what did we do this order in? Dx, dy, dz? It doesn't really matter though. Mass is now that. Now instead of integrating one, we're integrating that. Now that's a lot harder to do the Math 125 way. You'd probably have to do 2 separate problems if you wanted to do that. So there are things that make triple integrals more powerful. Volume may or may not be one of them. And I'll show a couple more videos of that.